Anahita Hosseinkhani. I have recently graduated in Master Science from Behnam University of Kerman. My supervisor is Dr. Behnam Ghavami, and I want to present my article, Improving Software Reliability of FPGA-based Deep Neural Networks with Reduced Approximate TMR. Deep neural networks are used as the foundation for many artificial intelligence applications like speech recognition, image recognition, and also in lots of safety critical applications such as autonomous driving, cancer detection, and space exploration. These applications are trained to identify objects based on capture frames and various signals. Superior accuracy of this application stems from high computational complexity. Neurons and layers are innately parallel, causing effective implementation of neural network in FPGA. But FPGA are vulnerable to single event offsets, which are induced by energized particles in the environment. So cells are able to change the configuration of lookup table or block RAM and routing connection in FPGAs. When the task is safety critical, reliability is crucial and has to be evaluated. So fault-tolerant techniques have to be applied to increase reliability. One of the most techniques for mitigation the effect of single event offset is triple module redundancy or TMR. In this study, the reliability of deep neural network, which implemented in a SRAM-based FPGA, has been evaluated through fault injection simulation. As a case study, we consider MNIST deep neural network, which have 5-layer fully connected topology. Vivado and Model Sim have been used for synthesizing network and simulating faults. Our topology consists of 784 pixels in layer 1, 13 neurons in layer 2 and 3, and 10 neurons in layer 4 and 5. The output of this network recognizes handwritten digits. So, for evaluating the vulnerability of this network, fault injection has been used. Faults injects into the random lookup table in neuron of each layer. As we can see the pseudocode of fault injection, after preparing the array of random lookup table, fault injection will start by bit flip in a specific lookup table. The simulation will be starts, and the detected output will compare with the expected output. And this process will continue until the last fault injection is completed. As we said, when the task is safety critical, the reliability role an important part. Triple module redundancy can be used for mitigation the error, but in deep neural network, due to high computational complexity, will add overhead in terms of power and area consumption. So adding this overhead is not efficient. So we mitigate the effect of single event offset in this network by protecting the most vulnerable layer, which is layer 1 in our study. With our purpose method, first sensitive lookup tables are identified through fault injection results. Then these sensitive lookup tables are separated into two groups. The first one, critical lookup tables, and the second, less critical lookup tables. Critical lookup tables including lookup table with 1, 2, and 3 inputs. These lookup tables have been hardened against single event offset using TMR. Less critical lookup tables, lookup table with 4, 5, and 6 input, which bit flip in one bit of this lookup table does not affect the output of our purpose deep neural network too much. These lookup tables have 16, 32, and 64 output bits respectively. Approximate logic circuit was used to reduce this configuration bits. Triple major redundancy or TMR. In this method, 3 copies of the circuit are prepared and a volter is placed at the end of these similar circuits. Approximate logic circuit is actually a circuit that has a different logic function but close to the main circuit so that it can use error detection and correction operation in the part that overlaps with the original circuit. So we use these two solutions for mitigating the effects of SEO in our topologies. We compare the following configuration for MNIST deep neural networks. The first, original, the MNIST DNN without any mitigation technique. The second, reduced approximate TMR, the DNN using triple major redundancy and approximate logic method. And the third, selective TMR, the DNN with a triplication of lookup table in sensitive layer, which is layer 1, and is evaluated in references 19 in our article. And actually we compare our purpose method with selective TMR that have been used until today. Results of fault injection in this study are divided into 3 categories. Normal, the detected output get after the fault injection is the same as the expected output. Wrong result, the detected output is contrary to the expected output. Timeout, this occurs when no results are obtained after several clocks. The primary results through our fault injection are expressed as architectural vulnerability factor, where the n is the number of errors and is the number of fault injections. As we can see, 99.16% of fault results are normal, while 0.4% of wrong outcome, wrong result, and timeout. As we said earlier, when the task is safety critical, reliability is crucial. And for deep neural network, which implemented in safety critical application, fault tolerant technique has to be applied. Figure shows the percentage of mask fault by each hardening design through their total number of utilized resources. It has to be noted that our method reached 14% fault masking with 8% increase in resource usage, while selective TMR reached 45% of fault masking with 13% increase in area. Hardening efficiency graph can be used to demonstrate the ratio between benefit fault masking and cost utilized resources of each design. As we can see, our method is 8% higher than selective TMR. As we said earlier, TMR will increase the power consumption. In this figure, power consumption in approximate method increase about 4%, and while in selective TMR, power consumption increase about 12%. So, the layers near the input, actually the hidden layer, the first hidden layer were responsible for the expressive discrepancy in the output. Applying our purpose hardening strategy to the right layer of MNIST DNN presented the best fault masking against area utilization. And also with our method, we can see considerable reduction in the power consumption. And finally, thank you for